In this section of notes, we're going to look at one more type of chi-squared test. Now, the test we've looked at so far is we looked at a test for goodness of fit. So we had some claimed distribution and we wanted to know if our sample matched that distribution. So the key there was one sample and one variable, like the M&Ms, and then the variable was what color the M&M was. And then we looked at a test for homogeneity. In that one, we had two samples and one variable, or maybe more than two samples. In our case, the samples were the different kind of musics being played at the different types of restaurants, and then what kind of entree they ordered. And now we're looking at the last chi-squared test. Sometimes this is called a test for independence, and sometimes it's called a test for association. Those are basically the same test. Now, in terms of the mechanics, this is absolutely identical to the homogeneity test. It's just that your hypotheses are a little bit different and then your conclusion is a little bit different. But the rest of the state plan do conclude procedure is the same. In terms of the conditions we're checking, the conditions are the same. So we still want our sample to be a random sample or to come from an experiment where we used random assignment. If we picked a sample, we still want to check that our sample size is less than 1/10 of the population size, and we still have our expected counts, and we want all of those numbers to be greater than 10. The main difference is sort of like in previous units where we looked at 1 proportion z-tests and 2 proportion z-tests, where when it was a 2 proportion test, we wanted independent random samples rather than just random samples. So we wanted the 2 samples to be independent of each other. That's kind of the same thing between the differences between the random for independence and the random for homogeneity. So in homogeneity, you're taking from more than 1 sample, so you want those samples to be independent random samples. For independence or association, you're just taking from 1 population, so it can't be independent of itself. It's just a plain random sample. So again, most of the mechanics are the same. Our formula for our test statistic is the same. Our formula for the degrees of freedom is the same. The thing that's different is our null and alternative hypothesis. For our null hypothesis, we can either say there is no association between the 2 categorical variables that we're interested in, or another way to say that would be to say that the distribution for those is independent of each other. So that would be the same thing. And then our alternative is that they are dependent or there is an association. So here's our example. We have a group of people split into male and female, and whether or not they showed fright symptoms while watching a scary movie. Now, in terms of the calculator commands that you learned in your last section of notes, where you take the observed counts and put them into matrix A, you're doing the exact same thing here. So all of the mechanics are the same. This is computer output. So you can see within the computer output, you can see the observed counts and the expected counts. So the way that this test is different than the last one is that we only took 1 sample of people. So the way we know to use the test for independence or association is because we had 1 sample of people, and then we took those people and we broke them up by gender and whether or not they had fright symptoms. So that's how we know that we're going to use the independence or the association test rather than the homogeneity test. So we're first looking for a hypothesis, which would be our null hypothesis is that there's no association between gender and the fright symptoms they have while watching the scary movie. And then the alternative is that there is an association. Again, you could have said something the same, but using the word independence. So you would say that gender and fright symptoms are independent for the null, and they are dependent for the alternative. So as we look at the computer output, just like we did before, we can see The red highlighted parts, those were the observed counts. The blues were the expected counts. Again, you would get this from your calculator by running the chi-squared test after you put the observed counts into matrix A. And then you can see the test statistic, the degrees of freedom, and the p-value as well. So if we want to know which of these 4 areas, whether they were male and female and whether they had the fright symptoms, which one contributed the most, we're looking at the blue highlights and we're finding the largest number. So the males that had the fright symptoms were the biggest contributor. They had the largest part of the chi-squared statistic. Now, in terms of interpreting our p-value, that's the same as it has been throughout the course. So assuming that our null hypothesis is true, the p-value is the probability of getting a test statistic as extreme or more extreme purely by chance. So here we are, we're looking at our p-value of 0.045. So that's the probability of getting a distribution as extreme as ours or even more. And because that value is greater than our alpha value of 0.01, then that means that we failed to reject our null and we don't have convincing evidence that there's an association between gender and fright symptoms. Now notice if we changed our alpha value, then we might be in a different position in our conclusion, but based on our alpha value of 0.01, this is the conclusion we're making.